An important concept to be introduced to here is the flux form of a vector field. Now in R3, given a particular vector field that is 3 components because we're in R3, we can define a two-form field known as the flux form by the following. By taking the determinant of a 3 by 3 matrix where the first column is the vector field, the second column is V, and the third column is W. In terms of basis forms, this is what this looks like. V1 times dx2 wedge dx3, V2 times dx3 wedge dx1, plus V3 times dx1 wedge dx2. Now the properties of the determinant guarantee that this two-form is bilinear and antisymmetric in V and W. And in fact, this flux form is very, very useful. It has physical significance. If F happens to be a velocity vector field of a fluid, then this flux form represents the rate at which fluid is flowing through the small parallelogram that's spanned by V and W. And the integral of integrating this flux form over an entire surface would represent the rate at which fluid flows through the whole surface. Now, because in R3 a two-form field can always be expressed as the flux form of a vector field, it's possible and conventional to do electrostatics and magnetostatics using nothing but vector fields and never even mentioning two-form fields. So for instance, we could say that in Rn, given a vector field, right, n components because we're in Rn, we can define the n-1 form field, the flux form, by the following, where we take the determinant, we basically have the flux form act on the parallelogram spanned by 1 through n-1 vectors. That's also the determinant where the first column is F and the n-1 other columns are V1 through Vn-1. And an example from physics is the 3 form in R4 made from the vector field whose components are charge density and current density. We'll be computing a great deal of flux forms as we go through this chapter, and we'll be seeing these more and more in their connection to physical applications as we work through this unit.